Greeting to Dr. Maheza, and my name is Lim Ping Guan. I am from Section 1. In this presentation, I will show you the demonstration and analysis and discussion for the Passmark performance test. So before running the benchmark, I close all the unnecessary background application as shown in this task manager. And I connected the laptop to AC powered and selected the window best performance power mode to ensure more consistent benchmark result. Okay, so first for workload A, I open the CPU test section in Passmark performance test, and this CPU instruction suite include integer maths, floating point maths, and the sorting benchmark. And I click run to execute the benchmark one by one. So starting with integer maths. And now it's floating point maths. And the last one is sorting benchmark. Okay, so after the test completed, Passmark display the benchmark result in million operation per second for integer maths and floating point maths, and 1000 string per second for the sorting benchmark. So if you want to see the result, you can open the result, save the result as web, and the result will be displayed here with the unit. Next, for the workload B, is same as the workload A. We selected the CPU mark, and here is the floating point maths and the extended instruction SSE, which is also same as the vector instruction. So we also run these two benchmark. Okay, next is SSE. Okay, so after running the benchmark, the result is displayed here, and we save the result as web. So for the workload B, the benchmark result is displayed in this table and with the correct unit. So for the floating point maths is million operation per second, and for the extended instruction SSE is million matrices per second. So that's all the demonstration of the benchmark for workload A and workload B using the Passmark performance test. Now I will present the analysis and discussion for the 2-3 Passmark performance test. Passmark benchmark results may be different slightly each time the test is executed due to many factors. So in this presentation, I selected one benchmark run at random and used its result consistently for all the performance analysis, including MIPS estimation, CPI calculation, and ISA structural bottleneck analysis. First, I will discuss workload A. Workload A focuses on evaluating the CPU instruction suite by measuring 3 benchmarks: integer maths, floating point maths, and sorting. So these are the screenshot of the benchmark result of workload A. And this is the table of the benchmark result. And from this table, the integer maths test achieved 32,432.2 million operation per second. The floating point maths achieved 15,664.7 million operation per second, while the sorting achieved 15,962.3 thousand string per second. So to estimate the processor throughput, we calculate the million instruction per second, which is also called MIPS, using the formula. And this formula is operation per second divided by 1 million, or 10 power of 6. So based on this calculation, the integer maths benchmark achieved an estimated 32,432.2 MIPS, while the floating point maths achieved 15,664.7 MIPS. The sorting benchmark was not converted to MIPS because the result measured in 1000 string per second, which represent the application throughput instead of processor instruction throughput. Therefore, it is more appropriate for the architectural analysis rather than the MIPS estimation. And for the MIPS comparison, these two results indicate that the processor execute integer instruction much more efficiently than floating point instruction. Integer operations are handled by the arithmetic logical unit, which perform arithmetic and logical operation with relatively low computational complexity. And the floating point calculation require the floating point unit, or FPU, which perform more complex arithmetic operation, resulting in lower throughput. And next is cycle per instruction, or CPI analysis. So using the processor clock speed of 2.7951 GHz, we estimated the CPI using this formula: clock rate divided by instruction rate. So the estimated CPI for integer maths is calculated 0.086, and for the floating point maths is calculated 0.178. Okay, so for this CPI comparison, a lower CPI indicates that fewer processor clock cycles are required to execute each instruction. Therefore, the integer maths benchmark demonstrates better execution efficiency compared to floating point maths. The higher CPI for floating point operation reflects the additional execution stages and hardware complexity involved in processing decimal arithmetic. Okay, next I will explain about ISA structural bottleneck analysis. The integer maths benchmark show that the processor ALU can sustain a high instruction throughput with minimal execution bottleneck. And for the floating point maths, the throughput is lower than this integer maths, indicates the heavier utilization of the floating point unit, since floating point instruction require more computational specialized hardware resources. And for the sorting benchmark, performance depends not only on the CPU execution speed, but also on the cache hierarchy, branch prediction, accuracy rather than the raw execution speed. Overall, workload A demonstrates that the processor performed exceptional well for integer intensive workload while maintaining stable performance for floating point and memory intensive application. Now I will move on to workload B, and workload B focuses on evaluating the processor floating point unit performance and SIMD execution capability. So these are the screenshot of the Passmark performance test benchmark result. And this is the table of the benchmark result. So the floating point maths benchmark achieved 15,803.7 million operation per second, while the extended instruction SSE benchmark recorded 6,332.3 million matrices per second. The floating point maths result shows that the processor is capable of performing a large number of floating point calculation efficiently. This is particularly important for applications such as engineering simulation, scientific computing, multimedia processing, and machine learning. So the second benchmark evaluates the single instruction multiple data, which is SMID analysis. And SMID allows a single instruction to process multiple data elements simultaneously using vector instruction such as SSE, ABX, and ABX2. This significantly improves performance of workloads involving repetitively mathematical operation. The result of 6,332.3 million matrices per second indicates that the processor effectively utilized its SIMD execution units to accelerate vector-based computations. So this capability is especially beneficial for applications including image processing, video encoding, artificial intelligence, digital signal processing, and scientific simulation, where the same operation is repeatedly applied to the large dataset. Okay, so that's all for the analysis and discussion and the demonstration for the Passmark performance test. Thank you.